ওকে, হোপফুলি আজকেই তোমাদের লাস্ট ক্লাস। আর আজকে we're supposed to discuss the thermal conduction, but before going there I would like to mention one thing. I think I forgot to mention that. If I have, let's just consider that to be a recap. So when you have, let's say, 8 noded or 9 noded quad element, which means the sides are sorry 5, 6, 7 and 8, and let's say 9. So sides are all parabolic, okay, in either xi or eta. Okay, and let's say if you have an uniform traction in a given direction. Okay, so let's say this is a uniform traction. It may be along x, y or any arbitrary direction. Okay, but that is uniform. Okay, now now when you reduce this to the force vector for the same quadrilateral, so I am trying to discuss here something called consistent force vector. Okay, so what is a consistent force vector? Before going there, can you tell me, see, we know that any given traction through this integration n transpose t d gamma over gamma t would eventually become a force vector, right? And what is you think that this force vector should be? What do you think? How this force vector should be? How would this force, this distributed force, be? I mean, those would be nodal forces, right? So you'll end up having three forces at node number 2, 3 and 6. You'll end up having three forces. So you have F3, F6 and F9, F2 along the same direction, each of which obviously would be divided into x and y components, but I'm talking about the resultant force. Okay, and the way they appear in the force vector is also in terms of the components. But let's say, what about the resultant? What would be the ratio of the resultant force at each node? What would be the values of the nodal forces due to traction? Let's say the length of this side is L23, and let's say the uniform thickness is H. So what do you think this nodal forces should be? কারোর কিছু মনে হচ্ছে না?
স্যার এরিয়াটা মানে টোটাল যে গ্রাফ মানে যেটা মিডলে গোটাটা হবে আর কর্নারে 0 0 যদি হয়, মানে যেভাবে আমরা বিমের ক্ষেত্রে করি।
So the entire thing would be in the middle. Okay, তুমি বলছো পুরো জিনিসটা মিডলে থাকবে, মানে let's say the total traction is
1:2
T times H times L23 is the total traction, total force, right? The magnitude of the total force on this surface. You're saying that totally applies to over here. আচ্ছা, এটা একজন বললে এটা হবে না obviously, কারণ আমরা যখন বিমের ক্ষেত্রে ডিস্ট্রিবিউটেড লোডকে দেখাই যেরকম ভাবে, তখন যেটা ব্যাপার সেটা হচ্ছে দেখো বা আমরা একটা ডিস্ট্রিবিউটেড লোডকে একটা লোকেশনে, মানে একটা ডিস্ট্রিবিউটেড লোড রয়েছে, সেটাকে বিমের ক্ষেত্রে বলাটা ভুল। এটাকে আমরা দেখাতে পারি যে তার রেজাল্টেন্ট ফোর্সটা একটা জায়গা দিয়ে কাজ করছে। ওকে, কিন্তু এই যে রেজাল্টেন্ট ফোর্স যেটা মানে middle of the bar, let's say this is the distributed load, and there is acting on a, let's say, yeah, it can be a beam. Okay, and when we want to think of where the resultant of all of these forces is acting, yes, obviously, that is acting in the middle. Okay, if it is uniform, it is exactly acting in the middle. কিন্তু এখানে দুটো জিনিস বলা। এক নম্বর হচ্ছে যে যখন আমরা এই অ্যানালিসিসটা করেছি ইঞ্জিনিয়ারিং মেকানিক্সে, দেয়ার উই হ্যাভ কনসিডার্ড অনলি রিজিড বডিজ, উই ডিডন্ট থিঙ্ক অফ about deformation. Okay, and when we talk about resultant, it's a single force. Okay, we can reduce this system to a single force because it's a planar force system. We know that a planar force system or a parallel force system, we can eventually converge into a single force system. The equivalent can be a single force system, but that's the understanding from the first year, first semester. Okay, when you move on to strength of materials, you obviously have thought about deformation of the geometry, uh, and the thing is, yes, I agree that the net resultant force actually acts over there. Okay, বাট এই যে রেজাল্টেন্টটা, এটা শুধুমাত্র ফোর্সের রেজাল্টেন্ট, মানে এইভাবে তুমি রেজাল্টেন্টটাকে রিপ্রেজেন্ট করলে that only takes care of the net force in the system and the net moment in the system. It doesn't take care of, if the system actually deforms, it doesn't take care uh, uh, of the deformation. ওকে, মানে একটা ডিফর্মেবল বডির জন্য এটা ম্যাটার করে আমি এখানে কতটা ফোর্স দিচ্ছি বা এখানে কতটা ফোর্স দিচ্ছি, আদার দেন হাউ মাচ ইজ দ্য নেট রেজাল্টেন্ট অফ দ্য ফোর্স সিস্টেম। ওকে, তেমনি ফাইনাইট এলিমেন্টের ক্ষেত্রে আমরা দেখেছি যে আমরা একটা ডিস্ট্রিবিউটেড লোড নিলে, একটা ডিস্ট্রিবিউটেড লোড একটা বারের উপর দিলে, ওকে, এবং ধরা যাক সেই ডিস্ট্রিবিউটেড লোডটা কিউটা যদি ইউনিফর্ম হয়, okay, it would basically be two equal forces acting at the two ends in the same direction, by the way. Okay, so that would be symmetric, that would be same force. Okay, তেমনি ভাবে একটা ডিস্ট্রিবিউটেড লোড আমি যদি একটা বারের উপর এরকম নরমালি দিই, বা একটা বিমের উপর আমি নরমালি যদি দিই, ওকে, ইউনিফর্ম যদি হয়, ফাইনাইট এলিমেন্ট মেথডের ক্ষেত্রে that would eventually result into two equal forces and corresponding moments. Okay, কিন্তু এখানে একটা জিনিস বলার, সেটা হচ্ছে যে প্রথমত তো হচ্ছে এখানে আমাদের ডিফর্মেশনটা ইজ আন্ডার কনসিডারেশন, and the third thing is, here we are talking in terms of finite element method. Okay, যেখানে আমরা একটা নিউমেরিক্যাল মেথড ইউজ করছি এবং এখানে আমরা ট্র্যাকশনটাকে ওভার দ্য জিওমেট্রি ইন্টিগ্রেট করে একটা ফোর্স ভেক্টর পাই। Okay, and you probably have done some analysis with four noded quad element where you are supposed to get the force vector from the traction. Okay, but then the problem is, when you get the force vector, you might have realized for uniform traction that would be the same equal force at the two ends, right? So for uniform traction, it would be just the half of the total force on each node. Okay, but you see here, no force is actually applied in the middle. Okay, it's not about getting your rigid body version of your equivalent force system. You see, even if I get different forces at f2, f3 and f6, okay, the resultant of these three forces can still pass through node 6. Okay, obviously the resultant will have the same direction, and the resultant of these two forces, f2 plus f6 plus f3, has to be equal to this quantity. Okay, but the resultant may still pass through f6. Okay, but we are way past getting the correct resultant. Okay, here we'll have to position our forces just even to confirm with the deformation as well. Okay, so so in that way, in four noded quad element, the uniformly distributed load would eventually be distributed equally at the two nodes. Okay, but when it comes to uh, uh, three noded side, that means where the shape functions are parabolic. Okay, now obviously this f3 and f2 are not going to be zero, but what would be the values of f3, f2 and f6 with respect to the total value?
স্যার সবগুলো সেম হবে?
এটা একটা অ্যাসাম্পশন হতে পারে, ঠিক আছে, যে অ্যাকচুয়ালি আই এম জাস্ট I was just waiting for this answer, that f3 equals f2 equals f6 equals the total force due to traction divided by 3. Of course, in finite element method, the net integrated traction force should be same as the one given in the original problem. Okay, so we can write it like this. Okay, kintu that is what is our intuitive solution, or you can say the intuitive guess actually. Okay, so that is the guess we would make, because that's how we got for the four noded quad element equal values. Okay, but the thing is, in reality, since we are about to discuss a very different topic, so we are kind of running out of time, so I'm not going to the derivation, but obviously you'll find the derivation in the notes. Okay, but I'll right away give you the solution. The solution is the force would actually be divided into the ratio of 1:4:1. Okay, so basically over here, if 3 equals f2 equals would be your t times h times L23 divided by 6, whereas f6 would be 4 times this value, so eventually 2/3 th L23. Okay, and if you actually do this integration by taking the correct set of shape functions, you would actually get this answer. Okay, so that's why it is the consistent force vector. So that is the force vector you get out of, see, your finite element method is based on certain norms, certain quantities you are supposed to get through certain set of integration. Okay, in that you cannot simply put your intuitive understanding of the physical problem and simply put the uniform values of the force. Okay, so intuitive guess versus your consistent force vector is the situation is this, that your consistent force vector. Okay, so let's say this geometry is fixed at one end, another end it is being pulled. Okay, and if you apply a uniformly distributed load, you would expect an uniform uh, change in length everywhere. Okay, across this side. Okay, so that you would see if you use the consistent force vector. But instead, if you choose to have intuitive guess, okay, there the middle force would be slightly lower and the corner forces would be slightly higher, and because of that you would probably see uh, a deformation somewhat like this. Okay, so to have physical deformation, okay, so to have physical solutions from an uniformly distributed load or from any distributed load, okay, you are supposed to use the consistent force vector and not just simply use your intuition. Okay, because your intuition will not conform to the very method that is finite element method. Okay, so that way you get solutions like this. And how non-physical this solution is, you can understand when you assemble elements after elements. Okay, so for example, there are multiple elements being added. Okay, and let's say each of them are four noded quad element. So in the end, if all over the these sides, okay, if all of these sides are subject to the same uniform distributed load, so the force values would be of the ratio. Let's call this one as F star. Then this one would be 2F star. I'm talking about four noded quad element, 2F star, 2F star, and then F star. Okay. When it is a 9 noded quad element or an 8 noded quad element, then in the same situation, let's say with four elements, you are going to get, let's say, mm, over here is F star. Then in the middle, you will have 4F star. Now this corner node is associated with two elements. So here you will be having 2F star. Then again 4F star, 2F star, 4F star, 2F star, 4F star, and eventually F star. So it would be in the ratio 1 is to 2 is to 4 is to 2 is to 4 is to 2. Eventually 4 is to 2 is to 1. So only at the two ends it is 1. Everywhere else it is of this ratio. Okay. And actually, if you are familiar with Simpson's 1/3 rule, it basically is the same result. Okay, with Simpson's 1/3 rule of integration. Okay, it basically is the same rule. Okay, mm, so now you see how the distribution is very different from having uniform forces at each of the nodes. Okay, and you can imagine, just like the previous example, if you were to have uniform forces, okay, at each nodes, or sorry, at each node, if you were to have uniform force, same force, okay, what sort of deformation you can see. Okay, you would see very non-physical deformation. uh, so let's say over here it is too much stretched. Here also, here not so much. Then something like this. Okay, so a very non-physical set of deformation, it would be like this. Okay, so the entire surface would deform like this. Okay, and if you take a consistent force vector, that would deform, the surface would look smooth. Okay, even with the non-uniform distributed load. Okay, you would get a smooth deformation of the surface if you were to use consistent force vector, as in contrast to an intuitive case where you would get a very non-physical deformation. Okay, and that you do get this type of ratio, okay, even for the uniformly distributed load. Now you can imagine this is what you get with uniformly distributed load. If you take non-uniformly distributed load, okay, non-uniform distributed load, then you get very different force vector. Okay, so I need you to check this. So this is your first assignment of the day. So try this for uniformly distributed load for a 9 noded or 8 noded quad element. Okay, in transpose T, so you can take T to be some uniform Tx0 and check what sort of force vector do you get and what are the ratios of the nodal forces. Okay, so that is your first assignment. A of the বোঝা গেল?
Yes, sir.
Yes, sir.
Okay, so let's move on to our next topic, which is thermal conduction. So earlier we were looking into deformation of structures, okay, of deformable bodies. So what was our degree of freedom at each location? What were our degrees of freedom?
Sir, deflection.
Deflection or displacement u, which is a yes, which is a vector. Okay, so even in 2D it's a 2 cross 1 vector. Okay, what is our degree of freedom in thermal conduction? What is that is changing from one point to another as a degree of freedom? What do we want to evaluate once we are done the solution? What is the primary variable that we want to evaluate?
Temperature.
Temperature, which is a scalar. Okay, now this quantity strain, which is grad u plus grad u transpose divided by 2. What is the equivalent of that in the thermal conduction?
Temperature gradient.
Temperature gradient. Okay, so over here it's a matrix. Okay, and over here it's a vector. So this one is a matrix right there. Over here it's a vector. So as you can get a glimpse of this, that the thermal conduction problem is working on a lower level of tensors, and eventually it turns out to be a lot simpler. Okay, and also at each node, whether it is a 1D, 2D or 3D problem, you are only looking for one variable. Okay, whereas that changes with the displacement. Now the next quantity is the sorry. So in elasticity, you have the elasticity tensor. Okay, and it's a fourth order tensor actually. Okay, so what is the equivalent of that in thermal conduction? So
Conduction is
yes, the conductivity matrix. So it's a so this one is 3 cross 1. This one is 3 cross 3. Let's say this one is 3 cross 1. So this one is a matrix, 3 by 3 matrix. Okay, so you are not working with a fourth order tensor. That you'll have to eventually prove it, to be symmetric, and eventually bring it down to a 6 cross 6 matrix. We don't have that rigorous work to be done here. Here it is directly a matrix. Okay, now the next thing. Here you have stress. What do you have here in the right hand side in conduction?
Heat flux.
Heat flux. Now this quantity is a vector. Okay. Now heat flux, heat flow rate, there are different names to different quantities. I get confused often. Okay. There are two quantities. There is Q dot N, which basically gives you the heat flow rate per unit area, because this one is normal to a given surface. So that is how much is going past the surface. Okay. So let's say this is the heat flux Q, and Qn is the dot product Q dot N. Okay. Let's say this is the outward normal of the surface. Okay. And let's say this is the boundary to a given geometry. So this surface. Okay. So that is the outward normal, and that counts for whatever part of Q is normal to the surface. That actually eventually goes out of the system and becomes Qn. Okay. So that is the heat flow rate per unit area. Okay. So the unit of this should be, let's say, joules per meter squared per second. Okay. And unit of this quantity is also joule per meter square per second. This one, but this one is a vector. It is representing that what is the heat flow rate in each direction. Okay, at a given location. Okay. Obviously, the part that is parallel to the surface is not leaving the surface and remaining inside the geometry. So that doesn't count as Qn. So this quantity is a vector. Okay. And as the Fourier law suggests, that is k times grad of t. Over here, this quantity is d times epsilon. Okay. And don't be confused with the negative sign. Mm, it's there because if the temperature gradient is there, okay, so if the temperature is increasing, so if the temperature gradient is positive, that means the temperature, let's say, even within the geometry, if I can imagine an surface, mentally imagine an imaginary surface, okay, and let's say this side is left and this side is right. If at the right side, temperature is higher than the left side, so I would be experiencing a positive thermal gradient, temperature gradient. And then if the temperature in the right hand side is higher than the left hand side, in which direction would the heat flow? Left to right or right to left?
Right to left.
Right to left. Okay. Hence the negative sign. So if the temperature gradient is positive, heat flow is the negative. That's the idea. That's why there is a negative sign. Okay. And next comes your boundary conditions. By the way, you have your rho times B being the body force per unit volume. Okay. An equivalent of that would be heat generation. Again, this one is a vector. So this one is a scalar. Okay. And then let's say this quantity is your inertial part of the force per unit volume, which basically is the density times acceleration. Over here you have rho times Cp, the specific heat, and times the rate of change of temperature. Okay. Again, this side you have your first order derivative in time. Okay, not the second order. Okay. So of course, we would not be considering this second term right here, because we would be talking about static equilibrium problems. So would not be dealing with the quantities that change with time. Okay. So so this way we can also establish the boundary condition. Okay, in so there would be gamma T where the temperature would be given, and gamma Q where the heat flux would be given. Okay, or some convective boundary condition would be given. Okay, in gamma Q, and together they form your total boundary. Okay, and as you can imagine that at the same boundary you cannot put at the same location in the boundary you cannot put the flux boundary condition and temperature boundary condition. Okay, so this one is a null set. Mm, so just like the structural problems. Okay, so this is the equilibrium, or not the equilibrium equation, that is the equation for this is the equation. So this q is a vector. So I'm taking divergence of q. Earlier in the structural equation, I was supposed to take the divergence of stress. This time I'm taking the divergence of the heat flux vector, and 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 considering the heat generation, which is a scalar. So this is simply substituting for rho b, and this is simply substituting divergence of stress. So on the right hand side you are supposed to get rho u double dot. So here you would be getting rho cp t dot everywhere within the geometry, and your heat flux is actually, as we discussed earlier, minus k times gradient of t. Okay, and t is t is known as t bar, let's say, in gamma t, and on gamma q you have been given the you have been given the so we know that on gamma t for structural problem, sigma times n is some t external. Okay, some external traction that has been applied, that is sigma times n in gamma t. So that boundary condition we use for structural problem. Here that boundary condition would be an externally applied heat flux, and that externally applied heat flux is k times gradient of t times dot n. Okay, so if gradient of t is positive, if gradient of t is positive, heat is coming inside of the geometry. Okay, so times so gradient of t, so k gradient of t is a vector, k times gradient of t is another vector. You are taking the dot product of this vector with n, and eventually you are getting heat flux. But there is another term. This is the convective coefficient and t minus t infinity. Convection happening at the boundary. Okay, through through the ambient temperature, because the ambient temperature is different from the temperature at the boundary. Okay, so this is another term, that additional term that appears. Okay, because this concept was not there with the structural problem. This time you are encountering a new term in your equilibrium equation. Okay, when is it in an equilibrium equation? When I get rid of this term and say nothing is changing with time. Okay, that's when this forms a set of equilibrium equation along with the boundary conditions. Okay, so there is slight change in the boundary condition. Okay, এই part of the follow করা যাচ্ছে?
Yes, sir.
Yes, sir.
Yes, sir.
তো আমরা যেটা করব, will not be actually going to the entire discussion. So we'll form the variational form, and then we'll just discuss how we can implement that for various types of 2D elements. Okay, and that would be that. So first let's go for the variational form. So for that, let's assume v is an arbitrary variation. of t, and that means V equals 0 in gamma T. Don't confuse with this small t. That's not there in thermal conduction. Okay. So right now we are only discussing about a thermal problem. Okay. Now if you look at any finite element software of the current time, you'd see this word, let's say multiphysics, associated with them. I'm talking about COMSOL. I'm talking about ANSYS multiphysics. So everywhere you'd hear this term multiphysics. That means earlier we were discussing about the deformation of a geometry. So basically structural analysis, stress analysis, and then here we are talking about how the temperature changes through conduction and various boundary conditions. So there is these are two different physics. Okay, but does that mean they do not interact? That's not the case. There are times when they work with one another in a coupled or a decoupled way. Now, what is a decoupled way? I can give you an example. Let's say there are some micro electromechanical actuators, MEMS. You must have heard about micro electromechanical system, and to be hmm, contemporary with our time, we should also discuss about names where we go for the nanoscale. So there you can find there are actuators, MEMS actuator, which are operated through. So this is how the structure might look like. So you can imagine there is this rectangle, and then there is this tiny portion coming out of it, which connects to another rectangle and eventually connects to the wall. Okay, and what basically is done is you apply a voltage difference over here, delta V. Okay, across the two ends, so electric current flows. Okay, and as you might know that whenever an electric current flows through any conductor, that eventually gives rise to heat generation. So obviously it would be changing the temperature. Okay, but as you can see, this portion is narrow and this portion is wide, which means the electric current could be different in the two regions. Okay, because net electric current could be same, but the density of electric current would be higher somewhere and lower somewhere, which would mean that some portions will have uh, um, mm, higher heat generation per unit area compared to the other. That means here you'd see more heat generation per unit area or per unit volume compared to this area, which would result into what? Thermal elongation, which is associated with another coefficient which is called coefficient of thermal elongation. Okay, and with that you will see more deformation on this side, on the thinner side compared to the thicker side, and eventually the structure bends like this. This tiny structure bends like this and acts as an actuator. Okay, so it can switch on or switch off a system like this. So here what has happened, there is a uh, electric flow or electrical conduction, then there is thermal conduction, and then there is structural deformation. Okay, so this is a decoupled multiphysics analysis. Okay, and a coupled multiphysics analysis would be where the structural deformation will somehow affect the uh, the temperature distribution. Also, it might affect the distribution of the voltages. This this temperature change might result into change in resistivity and eventually affect the electric flow as well. Okay, so a lot of things might happen. So when you combine all of this, then you are doing a coupled multiphysics analysis. And as you can see, this is needless to say that the coupled analysis is a lot costlier than the decoupled analysis. Now let's stay in whatever we are discussing right now, which is thermal conduction. And we have mostly written down all the equations that we need: the main equilibrium equation, the differential equation, and also the boundary condition. So now hmm, let's get the variational statement. So what I'm doing here is I'm integrating over the domain v times whatever is our differential equation. And so the differential equation was divergence of q plus q equals 0. So what I'm doing here is I'm substituting for q as k times minus k times gradient of t. So I'm taking divergence of k matrix times gradient of t vector. Okay, so I'm taking a gradient which is a vector, multiplying k, again a vector, taking a divergence which is a scalar. I'm simply multiplying that scalar with another scalar called v. Okay, and then I need to take the other part as well, plus q, okay, d omega. Now this integration would be 0, but other than the boundaries, this is true everywhere within the domain of, or the volume, but at the boundary this may not be true. So I need to add boundary terms which look like this in gamma q. So I don't need to take care of gamma t, because for gamma t v is already 0, so that is there. So v times q minus h t minus t infinity. Okay, so this q is basically your externally applied heat flux. Okay, minus n dot, which we discussed earlier, k times gradient of t d gamma. This whole equation goes to 0. You might remember that for structural analysis as well, we took t minus sigma times n and took a dot product with v. Okay, so and then we integrated over gamma t and then d gamma. Okay, so this is that term from the variational statement of the structural analysis. The next thing that we would do is we would take the first term, okay, and in some way we would do the integration by parts by transferring the order of derivative. So you'd write v. So this is true. You need to mention this. This is true for all v. Okay, this is true for any arbitrary v. Now v times divergence of k times gradient of t is basically this quantity. It is v times summation over, so summation over I del xi of the following quantity, which is uh, k ij summation over j gradient of tj, which is del t del xj. Okay, and this quantity can be written as, since the summations go from go with the limit 1 to 3, they are, the limits are independent, and I can change the order, and this quantity can eventually be written as summation over I del xi of v times kij del t del xj minus summation over, so I can basically take v inside, summation over j del v. Yes, so basically if I were to expand this term, I'll have this term my plus another term, so that one I am subtracting. So del v del x del v del x I summation over I k I j del t del xj. So this together can be written as j goes from 1 to 3. Okay. So so the first term is v times divergence of k times grad of t, that is the left hand side, and that can be written as a sum of two terms. So the first term is taking the divergence of v times k times grad of t. Okay, so k times grad of t, as we discussed earlier, is already a vector because grad of t is a vector, k times grad of t another vector. So I'm multiplying a scalar to that and taking the so once I multiply with a scalar, this still is a vector. I'm taking the divergence of that, and then here I'm subtracting uh, another term which is grad of v, taking dot product with k times grad of t. Okay, so now if I substitute that to the this expression over here to over there, so this is what I get. So this is what I get, integration over the volume. So the first term is, okay, I can rearrange this. Okay, so that would be, so I'm writing the first term first, gradient of v taking dot product with k times grad of t, and then because q would be subtracted, q times v another term, okay, t omega plus the following. Achha. So I can write this, then I'll be having another term which is divergence of v k times grad of t, this whole thing, the divergence of that quantity, okay, times d omega plus another term which is the boundary term. So in gamma q, so whatever boundary term that we wrote earlier, so that would be there. So that would be v times q minus h t minus t infinity. Actually, we could come with a negative sign, t minus t infinity minus n dot k times grad of t d gamma. Okay, now if I look at this term, so this integration is over the volume, but I can use Gauss divergence theorem and represent that as the integration over the surface and the total surface gamma n dot v times k grad of t d gamma. But you need to remember that would be this gamma is actually gamma T plus, sorry, gamma T, that is the temperature, and gamma Q. Okay. Now what happens to this term in gamma T? Can you tell me? So the boundary term that we got from the second volumetric integral, okay. So a part of that would be in gamma T and part of that would be in gamma Q, because it's all over the boundary. Okay. Can you tell me what happens to the term in gamma T?
0.
Why is that?
Okay. The arbitrary variation is 0 in gamma T.
Because V is 0 in gamma T. So whatever this term is, because V is trivially 0 everywhere in gamma T, so this integration goes to 0 in gamma T. But in gamma Q, this is non-zero. But then this is exactly same as this term right here multiplied to V. Okay. And I'm not sure whether or not I have made a mistake with the negative sign. Okay. Let's assume that I have not. So, okay. Yeah, I did actually. So this one is actually a negative sign, right? So, so these two terms do cancel out. Okay. So this one is negative and this one is positive. These two cancel out. So I can get rid of these two. So this and this cancels out. So eventually I'm left with only few set of terms. Okay. So in the end, this is the variational form that I'm looking for. So it's going to be grad V dot K times grad of T d omega. Then I'm taking another term involving T from here, which is plus integration over gamma Q. You see, because uh, convection is unique to thermal conduction, okay, a unique type of boundary condition. So this type of term we didn't see with structural analysis. And this term, because it involves T, it will also contribute to the stiffness matrix. Okay. So T or a gradient of T, everything will always contribute to stiffness matrix. So V times H times, so minus V times H times T d gamma. Okay. So that forms the left hand side. And in the right hand side, you have integration over the volume QV d omega. That basically is the contribution of the variational part. And the body force part. Okay, that is equivalent to the body force. The heat generation over here is equivalent to body force. Okay, that is like having rho b. Okay, V transpose rho b is what you are seeing here, and eventually minus is it going to be a minus when it goes to the other side? No, I believe it's not minus, it's plus integration over gamma q v times q plus h times t infinity d gamma. Okay, so that's the final variational form for the thermal conduction. Okay, and this is what we are going to do. Let's say if we take a 4-noded quad element, okay, to do thermal analysis. Okay, so in that we can identify the different shape functions. The shape functions are going to remain the same. That is the only thing that is going to remain same. Okay, and your temperature at any location is this times T hat, where T hat is where T hat is this quantity T1, T2, T3, T4, this thing transpose. Okay. So your shape functions are going to be the same, and you already know what type of shape functions these are. So what do you do next is you need to calculate gradient of the shape functions with respect to the natural coordinates. Okay, and then you need to from that you need to get the Jacobian, and from that the Jacobian you need to get the gradient of the shape functions with respect to the physical coordinates. Once you have done this, you can get the B matrix from it, and the B matrix is going to be quite different than the previous one. Okay, so here we are doing a 2D analysis. So the gradient of temperature, okay, is going to be gradient of, sorry, no, T is not a vector. So gradient of T is going to be a 2 cross 1 vector. Okay, and because it's going to be a 2 cross 1 vector, here it is going to be 2 cross 4. Acha, this n vector also, it is going to be a 1 cross 4 vector, right? 1 cross 4 vector, because the 4 temperatures, and then eventually 1 temperature over here. Achha, here it is 2 cross 4 vector, 2 cross 4 matrix, and you need to populate B matrix according to this understanding that grad of T should be del T del X and del T del Y. Okay, that's what the grad of T should be. Okay, and okay, so similarly you can write again, because V is a scalar, we would treat this to be as a grad of V dot product. Gradient of V dot product basically means gradient of V transpose this quantity. So gradient of V is also V times V hat. Okay, so you can substitute for V transpose over here, and for wherever you see V, for example, here you see V times H times T. Okay, so so you can think of wherever you see V alone, not with the gradient, there you can think of V to be V transpose. Okay, so V transpose is basically, so just like T, V, the variation is also n times V hat, where V hat is V1, V2, V3, V4. So V transpose is V hat transpose times n transpose. So substitute that, and for T it is n times T hat. Okay, so and over here also it is n transpose, sorry, V transpose, V hat transpose, n transpose. Substitute that here, and same goes for over here. Okay, so once you do all of that, you probably get an expression like this. So okay, so you will be having an element stiffness matrix that would look like integration B transpose KB. K would be 2 cross 2 because we are doing it in 2D, and this one is 4 cross 2, and this one is 2 cross 4. So eventually this, and then you would be integrating from -1 to 1 and -1 to 1. So here comes your thickness. Let's say for thickness I am using small t. Okay, because h is the coefficient of convection, so I'm skipping that. This is a uniform thickness. Then determinant of Jacobian times d xi and d eta is this is one term contributing to the stiffness matrix. Then there will be another term, surface integral. So T comes here, and I'll not put T, okay, because I don't know. Acha, because I need to, so for integration over the boundary, you need to consider all four sides, and some of them are in natural coordinates parallel to xi direction, and some of them are parallel to eta direction. So though that would be a sum of actually over four sides. So I'm just keeping it in the surface integral format. So there is d gamma, and basically you have h times n transpose in d gamma is what would be a part of your stiffness matrix. Okay, from the left side v hat transpose is multiplied, from the right hand side t hat would be multiplied, but then t hat multiplies to every term in the stiffness matrix. So this is what the expression of the stiffness matrix should be. Next comes your force vector. The force vector, other than the reaction force vector, or now what would be reaction in case of thermal analysis? At each node, wherever we know the temperature, there is an unknown heat flow rate. That is the scalar Q. Okay, unknown scalar Q. Okay, basically the reaction heat flow rate QR acting at each node wherever we know the temperature. If the temperature is known, then this QR is not known at that node. So this is the vector of that quantity, and then you have one part for the distributed load, which is distributed traction load, which is your uh, h times t infinity plus q external applied. Okay, and this whole thing you need to multiply with n transpose and integrate over d gamma in gamma q at whichever surface there is a heat flux boundary condition. There you are supposed to do the integration. Let's say here I'm applying a heat flux boundary condition, then you are supposed to integrate over there. And for the body force part or heat generation part, you have n transpose times q. Now this q or this h times t infinity, all of these are scalars. So basically you are getting a vector out of it. Actually this n transpose has appeared because of the v term, the variation term. Okay, basically converting into v transpose n transpose. So this quantity also give you, so this gives you the uh, force vector coming from the body force, and this is the force vector coming from the boundaries, that is convection, and also from the externally applied heat flux. Okay, so that's all that is there. So your second assignment is to do this exercise for a to find out each of these terms. Okay, for so symbolically get each of these terms, okay, in the thermal conduction for a square element of each side of length a. So that way you know the Jacobian itself is a by 2 times the identity matrix. Okay, so I know that the four-noded quad element is very difficult to integrate because there would be linear terms of xi and eta in the B matrix, even with a square-shaped element where the Jacobian is very simple. But since we are only working with a 3 by 3 or 2 by 2 matrix here, look at K here, it's a 2 by 2 matrix. I think you can do that integration. You don't have to use any numerical integration scheme or anything. Just simply do the integration. It's a lot simpler set of calculations, because if you are working with displacement degrees of freedom, then the B matrix should be 8 cross 2 cross 3 cross 8. So huge size, 3 cross 8, and matrix in the center would be the elasticity tensor, which would be 3 cross 3. So eventually the total product matrix should be 8 cross 8, but here you would be working with a 4 cross 4 matrix. So I think it's a lot simpler problem for you to integrate. So the second assignment of the day is to evaluate each of these terms symbolically. Okay, for a four-noded quad element. Okay, so এই অবধি বোঝা গেল?
Yes, sir.
কোনো কনফিউশন?
No, sir.
ওকে, তোমাদের বোধহয় 6 তারিখ থেকে পরীক্ষা হওয়ার কথা বা এরকম কিছু একটা ব্যাপার আছে, তাই না? সেমিস্টার এক্সাম।
শুনছিলাম তো এটা কেউ পেছাবে।
আচ্ছা, যাই হোক না কেন, ভোটের জন্য হয়তো পেছাতে পারে বা কিছু, হোয়াট এভার দ্য কেস মে বি, meanwhile if you develop any confusion, okay, regarding any topic, okay, so each of you would be having your own set of confusion or doubts, okay, so what we can do is, even in the next week, one of the days in the next week, we can sit together and discuss about whatever queries you might have. ঠিক আছে?
স্যার ওকে স্যার।
ওকে, তো আজকে যে অ্যাসাইনমেন্ট দুটো দিলাম, একটা তো সিম্পল, ফর কোয়াড্রেটিক শেপ ফাংশন, গেট দ্য ফোর্স ভেক্টর, কনসিস্টেন্ট ফোর্স ভেক্টর। সো সেটা তো করতেই হবে, সেটা করে ফেলবে, বিকজ আই মাইট গিভ দ্যাট অলসো ইন দ্য সেমিস্টার এক্সাম, বাট দিস ওয়ান এইটা করতে পারা যাবে বলে মনে হচ্ছে, মানে কন্ডাকশন প্রবলেমের জন্য, টু এভালুয়েট the stiffness matrix and the force vector, এটা করতে পারা যাবে বলে মনে হচ্ছে।
চেষ্টা করব।
ওকে, তাহলে চেষ্টা করো। ইফ ইউ হ্যাভ এনি,
নোটসে কি দেওয়া আছে? নোটসে মানে নেই।
নোটসে কিন্তু ইন্টিগ্রেট করে দেওয়া নেই, নোটসে এই আউটলাইনটাই দেওয়া আছে।
ওকে, আচ্ছা আচ্ছা,
ঠিক আছে, নোটসে এই আউটলাইনটা পুরোটাই দেওয়া আছে, যদি কোনো কনফিউশন হয় নোটসেও দেখতে পারো, and try on your to try it on your own and let me know if you have any problem. Okay.